Let's continue our study of nuclei. If we consider the nucleus of the simplest element, hydrogen, it consists of only a single proton. However, if we move to the second simplest element, helium, its nucleus contains two protons and two neutrons clustered together. If two positive charges are as close together as they are in a nucleus, they will repel one another with a very strong electrostatic force. We can use Coulomb's law to calculate the magnitude of the electrostatic repulsive force between two protons separated by a typical distance in a nucleus, say 1 femtometer. We find the force is approximately 230 newtons. What, then, keeps the nucleus from flying apart? Clearly, there must be an attractive force that holds the nucleus together, since many naturally occurring atoms contain stable nuclei. One attractive force that we have studied previously is the gravitational force. We know every mass in the universe is attracted to every other mass through Newton's universal law of gravitation. Let's use this relationship to calculate the attractive force between two protons due to gravity. We find this force is approximately 2 times 10 to the minus 34 newtons. Wow, this is an incredibly small force. Clearly, gravity is not the force that holds the nucleus together. In fact, there is a new force, called the strong nuclear force, that is responsible for the stability of the nucleus. The strong nuclear force is one of the three fundamental forces that have been discovered. Fundamental in the sense that all forces in nature can be explained in terms of these three. The gravitational force is also one, as is the electroweak force. Let's look at the important characteristics of the strong nuclear force. First, it is independent of electric charge. At a given separation distance, the attractive force between two protons is the same as it is between two neutrons, or between a proton and a neutron. Second, the range of the strong nuclear force is incredibly short. The force of attraction between two nucleons is extremely strong for distances on the order of 10 to the minus 15 meters, and essentially zero at greater distances. In contrast, since the electric force between two protons drops off as 1 over r squared, it decreases to zero only gradually as the separation distance increases to large values, and therefore it has a relatively long range of action. The limited range of the strong nuclear force plays an important role in the stability of the nucleus. For a nucleus to be stable, the electrostatic repulsion between the protons must be balanced by the attraction between the nucleons due to the strong nuclear force. Since the electrostatic force has such a long range, each proton repels all other protons within the nucleus. In contrast, however, any one proton, or neutron, is attracted to other protons and neutrons that are only its nearest neighbors, due to the short range of the strong nuclear force. As the number z of protons in the nucleus increases under these conditions, they all continue to repel each other electrostatically. Thus, the number n of neutrons has to increase even more if stability is to be maintained. The figure shows a famous plot of n versus z for naturally occurring elements that have stable nuclei. For reference, the plot also includes the straight line that represents the condition n equals z. With few exceptions, the points representing stable nuclei fall above this reference line, reflecting the fact that the number of neutrons becomes greater than the number of protons as the atomic number z increases. As we continue to move down the periodic table of elements, more and more protons are added to the nucleus, and there comes a point when the balance of repulsive and attractive forces cannot be maintained by any increased number of neutrons. Eventually, the limited range of the strong nuclear force prevents extra neutrons from balancing the long-range electrostatic repulsion of extra protons. The stable nucleus with the largest number of protons occurs for z equals 83, which is bismuth 209. This stable nucleus contains 126 neutrons. All nuclei with more than 83 protons, for example uranium with z equals 92, are unstable and spontaneously break apart or rearrange their internal structures as time passes. This spontaneous disintegration or rearrangement of internal structure is called radioactivity. It was first discovered in 1896 by the French physicist Antoine Becquerel. We will study radioactivity in a later section of this chapter.